Okay, in this next example, we have in the denominator a sum of squares. So this screams to us trigonometric substitution. So what's our trig substitution going to be? Well, it's the sum of squares. So we're going to take x to be 3 tan theta. So dx is 3 secant squared theta d theta. And so what does our integral become? Well, it's the integral of 1 over, and that was, we can rewrite the bottom as 3 halves, so that's an x squared plus 9 to the power of 3 halves. But an x squared plus 9, the reason we chose our substitution of tangent was because that would simplify. So x squared plus 9 is 9 tan squared plus 9, or 9 times tan squared plus 1, or 9 secant squared theta. And that was to the power of 3 halves, and then our dx becomes 3 secant squared theta d theta. And so this becomes, well, 9 to the 3 halves is square root of 9 cubed, so that's 27 in the denominator. With the 3 in the numerator, that becomes a 1 over 9. So that takes care of that. Constants, 9 and 3. Secant squared in the denominator, raised to the power of 3 halves, becomes secant cubed. Cancels with 2 of them in the numerator to leave us with just a secant theta in the denominator. But a 1 over secant is just a cosine. And so that anti-differentiates then to sine theta. And now we've got to write everything back in terms of our variable x. And here's where we have to use our little right triangle. We know that tan of theta is x over 3. So this is 9 plus x squared. And so what's sine of theta? Sine of theta is x over square root of 9 plus x squared. So this becomes 1/9 x over square root of 9 plus x squared plus c. Let's look at part B. The integral from 1 to e ln of x over x dx. So here we notice that the logarithm has its derivative that also appears in the integrand. So this is a perfect candidate for doing a substitution. U is equal to ln of x, du is equal to 1 over x dx. It's a definite integral, so let's switch the limits as well. So our new integral is the integral from 0 to 1. Ln of x is u, and then the 1 over x dx is du. So this becomes 1/2 u squared from 0 to 1, or 1/2. In the next example, we have the antiderivative of cos squared 5x dx. Well, we have an identity that allows us to rewrite the square of a cosine function. That becomes 1/2 plus 1/2 cos of twice the argument. Original argument was 5x, so the new argument is 10x. And then anti-differentiating term by term, that becomes a 1/2 x plus a 20th sine 10x plus c. In the next example, the antiderivative of x cubed ln of x dx. Since it's easier to differentiate the logarithm than it typically is to integrate it, we're going to give it by parts a shot. Because if I can move the derivative from an x cubed onto the logarithm, then that becomes a 1 over x, and it seems that I'll be able to reduce this just to a power of x, an integration of a power of x. So we're going to take the logarithm as the u. dv is going to be x cubed dx. So du is equal to 1 over x. v is equal to 1/4 x to the 4th. And this becomes then 1/4 x to the fourth ln of x. Remember, it's the product of these two minus the product of those two. So this would be minus the integral of the product of those two, which would be 1/4 x cubed dx, which is 1/4 x to the fourth ln of x minus 1/16 x to the fourth plus c. The next example is the integral of x secant x squared tan x squared dx. And since the derivative of x squared appears in the integrand as well, then we should first do a substitution. So this becomes then 1/2 the integral of secant u tan u du. And the antiderivative of secant u tan u, well, that's just secant of u. And so this is 1/2 secant of x squared, putting everything back in terms of x, plus c. And the last one in this group of integrals is the integral of the rational function 3x plus 1 over x times x plus 1. And so this means we should go to work on it using partial fractions, since it is a rational function. And so what is 3x plus 1 over x times x plus 1 as a sum of rational functions? Well, one has x in the denominator, the other one has x plus 1. They're linear in the denominator, so the numerator should be some constants a and b, multiplying through by the denominators. We get this relationship, or 3x plus 1 is equal to a plus b x plus a. Again, comparing coefficients tells us that a is 1, and b, well, a plus b has to be 3, and if a is already 1, then b has to be 2. Alternatively, another way to do this, rather than comparing coefficients, is to just look back at the original expression you get after clearing denominators, and just pick some values. If this is to be true for all values of x, pick some values which it simplifies nicely. So for example, when x equals 0, if I plug 0 into the left side, I get 1. If I plug 0 into the right side, I get a. So a has to be 1. And similarly, if I plug -1 into both sides, I'm choosing -1 because that would make this term go to 0 and have only the b survive. So if I put -1 in, that gives me a negative b over here and a -2 over here. So -2 is negative b, or b is 2. So that was the other way you can pick out what a and b have to be. You can either write down the polynomial of the left side and the right side and compare coefficients, or you can pick some values of x, which gives you a way to eyeball what the a and b have to be. So our integral becomes the integral of 1 over x plus 2 over x plus 1 dx, and those just anti-differentiate to give us a couple of logarithms, 2 ln of x plus 1 plus c.